we come on to the third mysterious observation of the 19th century science. This observation was the element line spectrum. It was observed that the gas discharge tube, a tube filled with some atomic gas, some elemental gas, when they were actually subjected to some electric fields, they give off specific frequencies of light only. And it was also observed that different elements, the gas that was made up of, different elements actually give off different colors. So, all of these colors must have been some relationship. They have some sort of a relationship with the different values of energy. So, let us observe how this looks like. See, if you really allow white light, say from the sun or from a simple light source to fall via slits on a prism, this used to get split onto the screen in the form of a VIBGYOR. However, if you have metals, or non-metals in the gaseous state, and when their spectrum was recorded, you will see that there was no continuous change like this of color. Rather, there were discrete patterns, there were discrete lines that came with different colors. You can see that at a wavelength of say some 400 nanometers and up to say 700 nanometers, hydrogen atom gas, they actually showed these lines. When you go over to sodium, which is a metal, within this range, you can see only one bright yellow line coming over here. So these line spectra were observed in case of atoms. So what might have happened? So let us have a close look. So if I have a setup like this, where there is a high voltage setup in a discharge tube, there was a slit over here, there was a prism, and once this prism resolved these lines, it were observed that they were 1, 2, 3, 4 and so on, depending on the nature of the atoms used in this discharge tube, that there were certain discrete lines and there were absolutely no continuum. So these are the line spectra that actually emerged from different systems. See, this is for the hydrogen, this is for the mercury, this is for the sodium. So these were the excited atoms emitting light only at certain wavelengths, and the continuum structure was missing. So wavelengths emitted dependent on the element that was chosen within the discharge tube. So let us come to the simplest atom, the hydrogen line spectrum. Okay, so this is the bottom one is the hydrogen line spectrum. So Johann Balmer, who was essentially a school teacher, he actually observed this hydrogen line spectrum and he came up with an idea that, okay, this line spectrum, the wavelength associated with this, can be fit into a formula like this, where there is a constant known as the Rydberg constant over here, and there are two numbers, and these numbers were specifically integers, which we call as n1 and n2. The question was why such a formula could explain the appearance of the line spectra. So this problem was taken up in a later stage in 1913 by Niels Bohr. Bohr essentially adopted Planck's idea that energy can only be absorbed or emitted in terms of packets or in terms of quanta, and he could explain the fact that electrons in an atom can only occupy certain orbits corresponding to certain energies, and these electrons occupying these orbits were the allowed orbits, or they were the permitted orbits with certain allowed values of energy. And as I have just said, that Bohr essentially adopted Planck's idea, so Bohr maintained that energy is only absorbed or liberated in such a way that the electron moving from one of these allowed states, one of these allowed energy levels to another allowed energy level could either absorb h nu amount of energy or could give up h nu amount of energy. So, the energy absorbed or emitted, depending on whether promotion or demotion has taken place, can result in this formula. So, a value of the Rydberg constant was found out and it was obtained to be 2.18 into 10 to the power minus 18 joule. And if you can just see this formula, instead of N1 and N2, I have replaced it by Ni. That means the initial value of N and the final value of N. And these were integers representing the initial and the final energy levels associated with that atom. So, Bohr's model essentially was a planetary kind of a model with the nucleus in between, and since it's hydrogen, there is only one electron outside, and using this model, Bohr actually found out a theoretical estimate for the Rydberg constant Re. So, we have represented this Rh in terms of Re over here because this was the theoretically found estimate from the Bohr's model. Now, once these developments were taking place, so of those three mysteries that we were talking about, once these developments were in force, another person by the name of Louis de Broglie, he came up with the idea that okay, matter can have waves, matter can be explained, or the properties of matter can be wave-like. This was some sort of a very striking observation that de Broglie made. So, de Broglie's observation that light, just like light, which can be wave-like or photon, that means matter-like, similar observations were there for matter as well. That matter can be matter-like depending on what sort of experiment you are performing, and it can also be wave-like. And de Broglie essentially found out a formula for the wavelength associated with these matter waves, and it was found out that this wavelength was related to the Planck's constant h and the momentum, that means mass times the velocity of that matter particle, by this simple relation. This relation is known as the de Broglie relation. So, once these were there, so what we have observed in general is that all of these cases, starting from the black body radiation via photoelectric effect to Bohr's theory and lastly the de Broglie hypothesis, all of these actually contain something in common, the Planck's constant. So the Planck's constant was a very crucial universal constant that actually came up in the 19th century or in the early 20th century physics that dictated a lot of things that were later to follow. So let us take up a simple exercise. So let us first calculate the matter wavelength lambda associated with a simple 1 gram ball. We see if you put the values of these constants over here, this 1 gram ball, let it be moving with a very simple velocity of 1 meters per second. So if you calculate, the corresponding wavelength came out to be of the order of 10 to the power minus 31 meters. Too small to observe. So this wavelength of everyday objects are really too small to measure. Just compare this with the corresponding de Broglie wavelength associated with a moving electron. Say a moving electron, which is a typical velocity of the order of say 10 to the power 6 meters per second and has a mass of this gram 10 to the power minus 28 grams, you can observe that the value of the corresponding de Broglie wavelength comes out to be just 10 to the power minus 10 meter or 1.1 nanometer. So this is almost of the wavelength of the X-rays. So they are much bigger. Thus, this entire idea of matter waves that actually generated some experimental technique which we today call as the electron microscopy, and this electron microscopy helped us look into small things. See, this is an electron micrograph of a very important thing. These these circular disc-like things are the HIV virus of the size of 100 nanometer, and these are the T lymphocytes. You can just see how this HIV virus gets into these T lymphocytes, breaking the wall of these T lymphocytes inside. So all this has been possible as a consequence of the idea of matter waves. Another very important consequence, another very important finding, which was completely a theoretical finding that came up during this time, the early 20th century, was the uncertainty principle by Werner Heisenberg. Heisenberg showed, or he actually postulated the fact that it is very difficult to simultaneously, it is actually impossible to simultaneously and precisely determine the position and the momentum of a dynamic microparticle. So what does this mean? This means that when you have a moving microparticle, say a moving electron, it will be impossible for us to simultaneously, that means at the same time, determine exactly with infinite precision. I mean, when I say exact, it means infinite precision, the value of its position, where it is located in three-dimensional space, and simultaneously the value of its momentum at that particular location. So this was in contrast with the classical observation that all objects whose forces are known, their positions and their velocities or momenta can be determined. So, Heisenberg uncertainty principle, de Broglie hypothesis, and the earlier observations actually led to believe that there is some sort of a wave-particle duality of matter. So this is a very important point, that matter can be wave-like, matter can be particle-like. Depending on what sort of experiment we are performing, matter at times behaves as waves, matter at other times, again depending on the nature of experiments that we are performing, behaves as particles. The same is true for the light as well, where you have a wave-particle duality. So, this uncertainty that Heisenberg has to say has a very important consequence in atomic structure. Let us move ahead. So, what we have observed till now, Planck's idea that energy is quantized, depends on frequency, Einstein's photoelectric effect, that the behavior of light is particle-like, the line spectrum, and the Bohr's model, that the potential energy of electrons are quantized, de Broglie hypothesis, which actually brings in the idea of wave-particle duality, and later all of these points, all of these 5 points together led to the development of what we today know as the quantum mechanics. So, as we are dealing with waves and particles simultaneously, we have to be very sure of what kind of waves we are dealing with. So, the simplest kind of a wave is a standing wave. The wave associated with, say, a guitar string. These kind of waves have something in common. The two locations in between which the wave is formed, you can see that if these two locations are separated by a distance of L, then this L distance can be spanned always by an integral number n of half wavelengths associated with the corresponding standing wave. This idea has a very important consequence. So, it was observed that every electron can be explained using some sort of a standing wave equation, and that expression led to the idea of a wave function. There is a quantized frequency which corresponds to the quantized energy. This actually were reminiscent of the ideas of de Broglie and Planck. And there were certain critical values assigned to this entire description, and these critical values or integral values were known as the quantum numbers. So, quantum mechanics essentially led to the idea of quantization of energy in a full-blown form, and in addition to that, coupled with the idea of Heisenberg's uncertainty principle and the mathematical description that was developed in quantum mechanics, led to the concrete idea of atomic structure. So, when we move ahead, we will very soon see that this entire idea of quantum mechanics, has a very firm foundation in the old quantum theory. That means the simple experiments that were there, the photoelectric effect, the black body radiation, and so on. These ideas essentially took a shape in the form of quantum mechanics, and what we observe will be very simple. So, Heisenberg's equation, Bohr's theory, and later Schrodinger's model, they were all certain complex mathematical equations, and with the help of these, we are going to establish the idea of atomic structure. So, first of all, if we move ahead, we see that quantum mechanics can also be termed as wave mechanics because it has something to do with the motion of waves. Secondly, an important thing that we must specifically point out that since it's a wave, it's diffuse, it's spread out in space, so there is absolutely no point in trying to locate a particular particle within that wave. Rather, let us take up a probabilistic interpretation associated with it. We will say that there is a specific probability, that there is a specific chance or a likelihood to determine the particular particle within a definite space, within a definite volume. And once quantum mechanics came into force, the idea of Schrodinger equation, the dynamical equation of quantum mechanics, just like the Newtonian model in classical mechanics, actually tried to explain the entire dynamical behavior associated with a dynamical microparticle. So one must keep in mind the fact that quantum mechanics in no way is trying to replace classical mechanics. Rather, the aim of quantum mechanics is to complement the shortcomings of classical mechanics that were there within the domain of microscopic particles. So this is essentially the Schrodinger equation written in the spherical polar coordinates for the simplest atom, hydrogen. See, here I have used a term Z which represents the nuclear charge. In case of hydrogen atom, this is 1, so you can simply drop this term Z when you are specifically dealing with the hydrogen atom.